In this video, we're going to learn about kinetic molecular theory. Kinetic molecular theory is a scientific theory that is used to describe the states of matter, solid, liquid, and gas, and how they transform into one another. In this lesson, we're going to visualize solids, liquids, and gases at the molecular level. We're going to describe solid, liquids, and gases based on their shape and their volume. And then finally, we're going to use kinetic molecular theory to understand ideal gases. Each video in this series is going to help us better understand gases and how they behave under certain conditions of pressure and temperature. Kinetic molecular theory is going to lay the groundwork for our understanding of gases. So let's begin with a definition of kinetic molecular theory. It really has two parts to it. The first part says matter is made up of particles, and then the second part says the particles are always moving. Now this goes for all matter. This little animation here would be what a gas looks like. The molecules or particles are spread out and they're moving pretty rapidly. Now this theory is going to describe the amount of kinetic energy that these particles possess. And so we have to understand what kinetic energy means. Kinetic energy is the energy of movement. And so the more kinetic energy a particle has, the faster it will move, and the less kinetic energy it has, the slower it's going to move. And we know that these particles are called atoms and molecules. So that's kind of the groundwork before we move on and looking at solid, liquids, and gases. So let's start with solids. And what we want to do here is zoom in on the particles of a chunk of matter. Let's say one of these ice cubes here in this glass of water. So if we could zoom in on these particles, we could see kind of what they're doing. Now the molecules of water are just represented by these little tiny spheres here. And they would just be kind of vibrating in place. They're moving slowly because they only have a little bit of kinetic energy. So solids have a low amount of kinetic energy. And one thing we have to remember is that every particle is going to have some degree of attraction with the other particles. And so they have to be moving fast enough in order to break away from the other particles. Now we call these attractions intermolecular forces. And that means the forces of attraction between molecules. So let's describe these particles in the solid chunk of ice. They're in a nice ordered pattern, and we would call this a crystal structure, or in other words, a crystalline structure. That just means there's a nice pattern to the way that they're organized. Solids also have a definite shape. In other words, if we were to drop an ice cube into a glass of water, it's going to retain its shape. It's still going to look like an ice cube. We could also say that the volume is definite. We could measure the height and the length and the width of this ice cube, and we can calculate its volume. So the volume is going to stay the same. So let's recap what we've learned about solids. The particles in solids are going to have a nice ordered pattern. The particles are going to be vibrating. They're moving slowly because they only have a small amount of kinetic energy. They have a definite shape and a definite volume. Okay, let's take a look at the particles of a liquid. This time we're going to zoom in on the liquid water here and look at what its particles are doing. In a liquid, the particles have much greater kinetic energy. They're going to be moving a lot faster. Now, they are randomly moving, so they don't have that nice ordered pattern, but they're not moving fast enough to break those attractive forces. They have the ability to flow past one another, and liquids are not going to have a definite shape, and so they're going to conform to the shape of the container that they're put into. I mean, you could pour a glass of water into a different shaped container, and it's going to fill that container and take on its shape. They do have a definite volume, and so we could use a measuring cup to measure the volume of a liquid. So let's recap liquids. Here's what we've learned. The motion of the particles of a liquid is going to be random. They're moving faster, they have more kinetic energy, and so they're able to flow past one another, but they don't have enough kinetic energy to break those attractive forces. They have an indefinite shape, which means they'll take on the shape of their container, but they do have a definite volume. Finally, we'll look at the water vapor, the gas state, and we'd have to boil the water and kind of zoom in on those particles and see what they look like. The particles of a gas will be moving very quickly. They're moving so quickly that the attractive forces really have no effect. They're very, very spread out and moving very randomly. Gas particles don't have a definite shape. They're going to fill the shape of a container just like a liquid. and they don't have a definite volume either. We can compress a gas into a smaller volume or let it expand to fill a large volume. So to recap what we know about gases, they move randomly and very, very quickly. They're so quick that the attractive forces are almost non-existent. They have an indefinite shape and an indefinite volume. Now, the rest of the lessons in this series are going to focus on gases. We're going to simplify our model of gases a little bit by ignoring a bit of reality. We're going to be studying ideal gases rather than real gases. Real gases are just a bit too complicated. So in order to study ideal gases, we have to make some assumptions. These are the assumptions we're going to make. The first one is that the gas particles are hard, round spheres. Now, this isn't reality because molecules come in all sorts of different shapes and sizes. The second point is that gas particles are not attracted to one another. Now, this isn't a crazy assumption because the particles go past each other so quickly that they don't really have time to feel those attractive forces. The third point is that gas particles do not take up any space themselves. Now, with this assumption, we'll take a look at kind of a little analogy here. I have a container here, and we'll say that we evacuated this container completely. We emptied it out. And this container has a volume of 500 milliliters. And so its empty space right now is 500 mils of empty space. Now, if I were to take some particles, say these ping pong balls right here, and drop them in, how much empty space would be left in that container? Well, it'd be 500 minus whatever these particles were taking up themselves. Now, the assumption we make with gas particles is that when we take gas particles and drop them in a container, the particles themselves don't take away from any of the empty space. We still have the same amount of volume inside that container. Now, it's not a crazy assumption because gas particles are so small. And here's the last assumption we make. It's that gas particles are going to collide perfectly elastically. Now, a perfect elastic collision means the particles will collide with each other and transfer their kinetic energy between each other. And so essentially the motion would be continual and forever. It's almost like if you were to hit a billiard ball and you hit the cue ball to break the balls, and the balls just never stopped. Ever. They just kept transferring their energy perfectly between each other and just kept on going indefinitely. And so these assumptions are going to kind of guide our understanding in the next lessons as we explore gases a little further. And so that is kinetic molecular theory.